All right, this is the final lesson of Unit 5, so Unit 5, Day 4. Today we'll be talking about complex and irrational roots. So I want to review quickly this for a minute from last unit. If we have a graph of a polynomial function, we can tell a lot about the number and the type of roots that that polynomial has. So remember that the number of complex roots is guaranteed to us by the fundamental theorem of algebra. If we have a degree 3 polynomial, we know that it will have exactly 3 complex roots. Now, of those complex roots, some of them are real and some of them are non-real. The graph can show you how many of those roots are real, and in this case we can see that there is one real root, and because it has 3 total roots and only one of them is real, that means it must have 2 that are non-real. The non-real roots don't show up on the graph of that function. They definitely influence the shape of the function, but there's no way to see them on the real coordinate plane. So this second polynomial, you can see that it's given to us as a degree 3 polynomial. And so that tells us, because of the fundamental theorem of algebra, that it has 3 complex roots. If we look at the graph of this, we can see 1, 2, 3 real roots. And that means that this function does not have any non-real roots. All 3 of the roots are real. Now in this case, if you look at those roots, one of those roots is an integer. It has a root of 6. But the other 2 are not integers, so we'll learn more about how to find those types of roots in a minute. This last polynomial is a degree 4 polynomial, so that means that it must have 4 complex roots. When we look at the graph of this function, if you look along the x-axis, there is actually no x-intercept, so this does not have any real roots. There are 0 real roots, and what that means is that they must all 4 be non-real. And we'll learn more today about how to find those non-real roots. Okay, so last time we worked with polynomials and we found the roots of a polynomial. A couple of times we had to sort of guess and check until we found one root, but most of the time I gave you one root or 1 0 or one factor and you used that one to find the others. Well, all of our answers last time lived in this category. They were all rational. We had roots like 2 or -5 or even fractions like 1/3 or something. But all of our solutions lived in the rational number world. Today, our solutions are going to be irrational. So we might have a solution like 2 plus √7 or something like that. And we also today will work with some that are imaginary, like maybe a root of 3i or something like that. So the process that we're going to use today is very, very similar to what we did last time. It's just that our solutions are going to be in these 2 other categories. Essentially today what we'll be working with is what if the polynomial is not factorable? And you probably remember from past units from last year that when we stumble upon these ones that are not factorable, we have to use a different strategy for solving them. So example 1, let's do this one. One of the roots of the polynomial equation is -2. What are the other roots of the equation? So again, I've given you the first root. We'll use that root to find the others. Well, we're given the root -2, so we can use some synthetic division with that. And there's no need to change the sign or anything. We know that the root is -2 and we use that root. I'm going to set it up with the coefficients. Again, those come from the coefficients of our polynomial. And now we'll just divide that. So we drop that first one down, and then we multiply by the -2 and put it in the next column. Add that column up. multiply by -2 and put it in the next column, add that column up, multiply by -2, put it in the next column, add that column up. Now I told you that -2 was a root of the function, so we should be expecting to get this zero remainder. And if you didn't get a zero remainder in this case, you would probably want to check your work and see if you could find an error. So when we completed the division, we ended up that this polynomial divided by the factor x plus 2 would give us an x squared plus a 2x minus 5. And this quadratic expression right here will give us the other two roots of the polynomial, but unfortunately, this is not factorable. And when things are not factorable, we have to turn to our old friend, the quadratic formula. So we identify what our a, b, and c values are. In this case, our a would be 1, our b is 2, and our c is -5. And so if we put those values into our formula, we get x equals -2 plus or minus 2 squared minus 4 times a times c, and that is all divided by 2 times a. So if we simplify this a bit, we end up with a -2 plus or minus the square root of, and we want to know what's inside that radical. Well, it's a 2 squared minus 4 times 1 times -5, and that simplifies to the number 24, and this is still divided by 2. Square root 24 is a radical that we can simplify. Root 24 is the same as root 4 times root 6. 24 is 4 times 6. We know the square root of 4 is 2, and so it simplifies to 2 root 6. So this is the same as -2 plus or minus 2 root 6 all over 2. And you might notice that we all these terms in the numerator have a factor of 2, so we can actually divide that 2 out. In the first term right here, it's a -2 over 2, so that reduces to -1. And in the second term, these 2's also reduce, so we have -1 plus or minus root 6. Those are the other roots of the function. And that's what it was asking us to find. What are the other roots? And we have found them. So I want to actually look for just a second at the graph of this function. Here it is. And you can see, let's see, on the other screen, we found that the roots were -2 and 1 plus or minus root 6. Well, the -2 you can see on the graph immediately. It's right here as the x-intercept -2. These other two zeros are also on the graph. 1 plus root 6 is about 1.45. That corresponds to this x-intercept. And the other one, 1 minus root 6, is also on the graph. It's approximately -3.45, so that is right here. So when you have irrational roots like this, they do show up on the graph. Those are real numbers. They just are not nice integers or nice fractions. They're irrational, but still a real number. You could find a decimal approximation for those, so they do show up on the graph. Okay, another one to try. So this time, though, we're given a factor. If we want to divide by the factor x minus 4, we use the 0, 4. And our coefficients are 1, -4, -7, and 28. So we divide this synthetically, drop the 1, multiply, add it up, multiply, add it up, multiply, add it up. So when we divide, we get the result x squared minus 7. We can use that quadratic formula with this quadratic. A would be 1, b is 0, and c is -7. So if we put that into our formula, we get -0, I guess, plus or minus 0 squared minus 4 times a times c, and we divide that by 2a. Well, 0 plus or minus something is really just the plus or minus something. And in this radical, it looks like we have 28, and that's divided by 2. Root 28 is the same as root 4 times root 7. So that's 2 root 7. So it's plus or minus 2 root 7 over 2. And those 2's can reduce. So we end up with x equals plus or minus root 7. Now if we read our question, it says, what are all the zeros of the function? It's asking us to list not just more zeros or some of the zeros, but all of the zeros. This is a cubic function. It's degree 3, so therefore it should have 3 roots. We've just found 2 of them, positive root 7 and negative root 7, and the third root is the one, the third zero, the third root is the one that we used here that corresponds with this given factor. The other one would be the number 4. So that gives us all 3 of the zeros of the function. Okay, so these irrational roots that have radicals that don't reduce, we find those using the quadratic formula. It's where we get those types of solutions from. And because of that, they always come in pairs. They're called conjugate pairs. If 1 plus root 2 is a root, I know that came from the quadratic formula, and I know also 1 minus root 2 is a root. When we're doing the quadratic formula, that would pop up as a 1 plus or minus root 2. So the positive and the negative one, they go together, they come as a pair. You will not have one without the other. At least nothing that we would see in this class. None of the polynomials we deal with will have anything like that. Or they'll always be in pairs. So if root 10 is a root, then also we would have negative root 10 as a root. If 2 minus root 6 is a root, then another root would be 2 plus root 6. It's always in pairs. And so in general, if a plus root b is a root, then we would also have a minus root b. So we can use this property if we know some of the roots to find other roots. For example, a polynomial equation with integer coefficients has the roots 1 plus root 3 and negative root 11. Find 2 additional roots. Well, automatically I know, since both of these are irrational, that they each have a pair that goes with them. If 1 plus root 3 is a root of the polynomial, 1 minus root 3 would also be a root of the polynomial. If negative root 11 is one of the roots, then we would also have positive root 11. And you don't have to write the positive sign there, but you can. We have a second question here. It says, what is the lowest degree of the polynomial? Lowest possible degree of the polynomial. Well, I know for sure that it has 4 roots. Number 1, number 2, number 3, and number 4. So it has at least 4 roots. Possibly there are other roots that I am not aware of or don't know about. But it has at least 4. So that means this polynomial has to be at least degree 4. All right, another one for you to try. And hopefully, as you read through this problem, polynomial equation with rational coefficients has roots 2 minus root 7 and root 5. Find 2 additional roots. Hopefully you identified 2 plus root 7 and negative root 5 as the 2 additional roots. One more example, a polynomial equation with rational coefficients has the roots 1 plus root 7 and 8. Do you know any additional roots? Well, this is an irrational root, so it definitely has a pair to go with it, a conjugate pair. And so we would have the root 1 minus root 7. However, the number 8 is not an irrational number, so it does not have a partner, so to speak. It can stand alone. there's no guaranteed -8 here. The guaranteed conjugate root only applies to these irrational ones. It has to have one of these radical parts that doesn't simplify. So I have 1, 2, 3 roots that I know. So the least possible degree of this polynomial would be degree 3. All right, a little comic for you. You can pause it and read it if you want. It's pretty funny. And now for something a bit more complex. Complex in terms of imaginary numbers. It's not any harder than it was before. We have a polynomial, and if you're following along in your notes, I did change this polynomial. Don't panic, it's just a different one. We have polynomial f of x shown here in this graph. It's a lovely function. I would like to know what the zeros of this function are. Well, if I'm asked the zeros of this function and I have this graph to look at, I can right away identify one of the zeros of the function, and it is -5. However, this is a degree 3 polynomial, so I should be expecting 3 zeros, but the only one I can identify from the graph is the number -5. Well, remember that we are definitely guaranteed 3 roots, 3 zeros. If we can only see one of them on the graph, that must mean that the other 2 are non-real. Non-real solutions or non-real roots are going to come from the quadratic formula. So we're going to use this root that we know, -5, and we're going to divide that factor of x plus 5 out. And if we do our synthetic division, multiply it, add it up, multiply it, add it up, multiply it, add it up. If we do our synthetic division, when we finish dividing, we have an x squared minus 4x plus 85. And that is not factorable. The only way to factor 85 is 5 times 17, I think. So there's no way to get that to add up to -4. But also the graph is sort of trying to show me that it's not going to factor. If it was factorable, I'd be able to see those roots. So if it's not factorable, I have to use the quadratic formula to solve it. So we'll identify our A and our B, -4, and our C is 85. And we'll use the quadratic formula. X equals -b plus or minus the square root of b squared. Be careful with that b, it should be inside parentheses, -4 times a times c, and that is all divided by 2 times a. And what we have in our radical, if we simplify that, we get x equals 4 plus or minus the square root is of -324, and that's all divided by 2. Let's see, make that a little bigger. Sorry. Oh, it's giant now. And 324, well, it's negative, so I know it's absolutely going to have an I. And if I think about the 324, well, let's just do that square root and see what it is. And hey, wow, the square root of 324 is just 18, so it's an 18i. And that's all divided by 2. Now, 2 is a factor of both the 4 and the 18, so I can go ahead and reduce that. It would reduce to a 2. The 4 over 2 is a 2. Plus or minus 18i over 2 is a 9i. Now, the original question here said, let's see, gotta go back. It said, what are the zeros of the function? Well, we identified that the first zero was -5. And then the other two are 2 plus 9i and 2 minus 9i. So we'll list all of those 3 zeros out. It was a cubic function. We were finding 3 zeros and we have found them. Okay, another one to try. So this time it gives me the 0, 2. So I'll divide synthetically here. Drop it down, multiply it, add it up, multiply it. Oh, you know, I just remembered that this has a typo. It needs to be a 70. I thought I fixed that, but apparently I didn't. So 58, multiply that, 116, add that up to be 0. Sorry about the typo. So we end up with x squared minus 6x plus 58. And that, we could try to factor it, but 58 is 29 times 2. And other than 58 times 1, that's the only way to get a 58. So neither of those combinations can add up to negative 6, so this is not factorable. So we have to use a quadratic formula. Whoops. A equals 1, B equals negative 6, C equals 58. So if we do the quadratic formula, we get x equals negative b plus or minus the square root of b squared minus 4ac, and that is all divided by 2a. So we have 6 plus or minus, our radical here is negative 196, so we know we're going to have an imaginary solution. So 196 happens to be, the square root of 196 happens to be 14, so this is the same as 6 plus or minus 14i over 2. And so if we reduce that factor of 2 out, we get 3 plus or minus 7i. Now this particular question just said what are the other zeros, so here are the other 2 zeros. The third one was given to us, so they were just saying find the other ones, which we did. All right, these complex solutions also come from the quadratic formula. So because of that, they always come in pairs as well. Were you noticing that they were coming in pairs? So if I have a 1 plus 2i that is a root of a polynomial, then I automatically know it also has a root of 1 minus 2i. If 7i is a root, I automatically know there's a negative 7i as well. If 2 minus 9i is a root, I know it has a root of 2 plus 9i. And if a plus bi is a root, I also know a minus bi is a root. They always, always, always come in pairs. So if a polynomial equation with real coefficients has 3i and negative 2 plus I among its roots, what other two roots must it have? Well, because it has a root of 3i, I know that it also has a root of negative 3i. Because it has a root of negative 2 plus I know it also has a root of negative 2 minus I. Now pay attention to the fact that only the imaginary part changed signs, not that negative 2. It stayed exactly the same. The integer part stays the same. The imaginary part changes signs. So a polynomial with integer coefficients has roots 3 minus I and 2i. Can you find two additional roots? I hope you identified 3 plus I and negative 2i as those two additional roots. All right, one last type of problem to look at today. A third degree polynomial equation with rational coefficients has roots of 7 and negative 3i. And we want to find this polynomial. Well, first of all, it says it's a third degree polynomial, but it only gives me two roots. There's another root that you should know automatically. I automatically know that because it has a root of negative 3i, it will also have a root of positive 3i. They always come in pairs. So for each of these roots, and I want to write a function here. So for each of these roots, I can write a factor to go with it. For the root 7, it has a factor of x minus 7. Because it has the root negative 3i, I know it has a factor of x plus 3i. Because it has a root of positive 3i, I know it has a factor of x minus 3i. So really, this is a function that has those particular roots. This function is in intercept form, though. I want to go ahead and put it into standard form. If you have a polynomial in intercept form, remember that to put it into standard form, you just have to multiply it out. Now, there is an easiest way to do this. I mean, you can do it a lot of ways, but the easiest way to do it is to select the two factors that have the i's and multiply those two together first, and then multiply by the x minus 7 second. So if we multiply these two factors that contain the 3i, we would get an x squared, a negative 3ix, a positive 3ix, and a negative 9i squared. So did you notice that we had a negative 3ix and a positive 3ix? Those terms reduced to 0. So we have x squared, and we also have this negative 9i squared, but we know that I squared is the same as negative 1. So this is really a negative 9 times a negative 1, which is a positive 9. Okay, so we've multiplied together those two terms. We still need to multiply by this x minus 7. And so we can FOIL that, multiply it out. We get an x to the third, a negative 7x squared, a 9x, and a negative 63. And so there's our function in standard form, all multiplied out. All right, just one to practice. We have a polynomial. It says it's a third degree polynomial, and it has a root of 3 and 2i. Well, it says it's a third degree polynomial, but we only have two roots. But actually, there is that other one that we know. Because it has a root of positive 2i, it also has a root of negative 2i. Now, for each of these roots, I can write a factor. The root 3 goes with the factor x minus 3. The root 2i goes with the factor x minus 2i. And a negative 2i root goes with the factor x plus 2i. So here's my function in intercept form. Let's put the function into standard form. Now again, you could start by multiplying these two together, but it's going to get really hard really fast. If you start with the two that have the imaginary part, it'll end up being much easier. You'll have some terms reduced. It just becomes much simpler. X squared plus 2ix minus 2ix, and then minus 4i squared. These two ix terms reduce to 0. One's positive 2 and one's negative 2. And we know that I squared is the same as negative 1. So this becomes an x squared plus 4. And then we need to times that by x minus 3 still. So if we finish multiplying this out, we get x to the third minus 3x squared plus a 4x and a minus 12. So here is our function f of x, we'll call it. And that has all of the roots that we needed it to have. Okay, we do have a super bonus challenge problem today. A polynomial with integer coefficients has roots 2 minus 5i, negative 3 minus 2i, 1 minus root 2, and negative root 7. What other roots must it have? So you need to write the conjugate for each of these. 2 plus 5i is another root. Negative 3 plus 2i is another root. 1 plus root 2 is another root. and another root would be root 7. And the final question, what is the least possible degree of the polynomial? Well, this thing would have to be at least, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I know 8 roots, it has to be at least degree 8. So that is it. We have review next time and we have test. If you are A day, your test will be Friday. If you are a B day, your test will be on Monday. Come see me if you need any help and I will help you.